All right, on to Objective 6.3. So here we're going to be calculating angles and distances on the ground using a map. So if you measure a distance on a map, you can determine the coordinates of the final location, as I'm reading this PowerPoint slide that you guys can read as well, if you have the original coordinates. So let's say you look at a map, you find that location, and then you need to navigate through that map using ground information or the coordinates of, if you have the distance and the angles. So you not only do you need to know two pieces of information in order to find your next coordinate, you may need to know three because you might need an original starting location, right? So you can also navigate through maps using ground information. So if, for example, they say, well, the distance on the ground is X, and your angle that we travel at is this particular angle, I now can still find it on the map and try to figure out where I'm going. So if you remember back, I don't know if any of you have had the opportunity to do orienteering, this is pretty much what it is. So the nice thing about angles is that they don't change. So whether it's on the piece of paper or it is in the field, they're still the same angle. The only difference is that if you use the map, the angle is just it's just not as big. So it's just taking that angle and making it, like, scaling it down to the smaller part. I don't actually apply a scale to it though. It stays the same. So 360 is always 360. So if you turn a circle in 360, is the same as the Earth going around in 360. There's just two different sizes. It's just one's on, for us, one's on a map and the other one is in real life. So we're just projecting it further as it says here. So just something to keep in mind there. So here's an example. We kind of did this in the last objective, but I'm just, again, trying to branch out a little bit further about how to do this. So if your starting point is at these values, the next location is that angle at a distance of this on the map. What are the coordinates of the next location? So like I said, the last objective, 6.2, I gave a written example of this. So we have my scale formula, 1 over s equals dm over dg, because we're going to try to figure out the ground distance here. So 1 over 25,000 equals 14.3 centimeters over dg, and we come up with our 357,500 centimeters, which is 3,575 meters, and that's the radius. The angle I'm going to convert into a decimal degree. So here I go from DMS to decimal degree. If your calculator can handle doing sine, cosine, and tangent, all with DMS, you don't have to convert it. But you need to make sure that your calculator can do that. If it can't, you just need to convert. So I'm trying to find x2 because it's the coordinates of the next location. I take my radius, I multiply it by the sine of the angle, and I add the first x value to it, which is the one we're given. So I put that in, and I find that my x2 is at 644,895 meters. And I'm going to double check to make sure that makes sense. So 195 degrees is past 180, so I know that it's going to be going around past the 180, so it has to be going backwards in the x. So does it reduce in values? So I see 645, and here's 644. So it has gone down. So I know that I'm heading in the right direction for this. Then y2 is the same, except this time around we use cos for my formula. And so the radius is 375. That doesn't change because it's still the same radius. And then times cos of the angle plus the 5.4 million. And then I get my answer. So it says it's 474,387 meters. Did it go down? Well, I see that it is 7,836 meters, and this is 4,387 meters. Does it make sense? Yes, it does. So please note that I am taking my time to check it, right? I take a look and think, does that make sense? I always suggest doing that. And there's many times I get answers from students and you can tell they didn't even think about it. They just like plugged some numbers and just like, I don't even know if they came up with numbers. So I don't know if they even understood the question because they just like jammed numbers in there. So make sure that you just take that time to look back and do that 2-second check. You saw me going, oh, okay, is that lower? Yes. Oh, is this one lower? Yes, it is. Okay, those make sense. Now, there still could be errors in it, but at least I'm taking the time to think about what I am doing. So that is that example. And so here we have some references for the images. Again, check it out. Go there, see what you can find. There's a lot of information online. There's even a coordinate converter that you can find. So you can give that a shot and see what that looks like. And so I do suggest, again, going through these references just because it does give you additional information on top of what I do. So that's all for 6.3. We will be moving on to 6.4 in the next video.